This isn't a typical skateboard. This is a skateboard that I designed and built and included features that allow it to ollie and do tricks like a kickflip on its own. In this video, I'll be showing you how I built this board, how the skateboard works, and I'll also be showing you test footage as well. So here's the concept. The skateboard trucks are mounted on hinge assemblies which drive the board into the air, and the motor-driven flywheel at the center of the skateboard can impart angular momentum into the board by starting or stopping its rotation mid-air. In order to actuate the hinge-mounted trucks, I chose to use pneumatic cylinders driven by solenoid valves. I needed to build some parts to see if this concept would work. I started by cutting out clearance holes for the pneumatic cylinders and the flywheel out of a spare skateboard deck. I made a template because I figured I'd be repeating this step on the next iteration. Next, I cut out some aluminum sheet metal and welded it together to create the truck hinge assemblies. I then mounted the trucks onto the board and installed the pneumatic cylinders to support some preliminary ollie testing. At first I was super disappointed at how low the ollies were from this thing because it didn't even have the rest of the components which would add to the total weight. I added some aluminum blocks to act as weights onto the skateboard to see how high it would ollie with a total mass more representative of the final configuration. I was surprised to see that it ollied significantly higher with more weight added. It's counterintuitive that the heavier it was, the higher it ollied. You can imagine the system like the pneumatic cylinder with a mass M1 at the top and a mass M2 at the bottom. The pneumatic cylinder actuation rate is limited by the pneumatic resistance of the solenoid valve itself as well as the lines between the air tank solenoid valve and pneumatic cylinder. The larger the proportion of M1 to M2, the higher the overall system will go in the air because the pneumatic cylinder will be launching it at a similar velocity somewhat regardless of these masses, within reason. I took a few measurements of the ollie height with respect to the skateboard deck mass, and you can see that as the proportional weight of the deck increases with respect to the truck hinge assembly, the ollie height increases until the point where the pneumatic cylinders are not powerful enough to accelerate the larger mass to the same velocity. So basically what we're trying to achieve is once those pneumatic actuators pop the skateboard up in the air, we have a finite amount of time before it's going to hit the ground, and the skateboard's going to have, 3 principal moments of inertia, 2 of which we're going to be trying to manipulate, and we might spin it about that axis or about that axis, but we want to basically spin up a counter-rotating mass using this 300 kV drone motor. I'll be using around 24 volts with 6S battery, and we'll be spinning up a flywheel. This was taken off of a centrifugal clutch for like a go-kart or something, and it was just something I didn't need for any other project anymore, and so we'll have to modify this a bit to mount up to this flywheel, but then hopefully we'll be able to do some testing with this motor and this flywheel, possibly adding some wheel balancing lead stick-on weights to the inside of the diameter of this flywheel in order to increase its moment of inertia. Basically my flywheel is out of balance and it's going to be causing a lot of vibrations throughout the board, and it's going to wear out the bearings in the drone motor a little bit fast. And so what I've done is set up a little neodymium magnet glued to the outside, and when that passes by this Hall effect sensor on this breadboard, I get a trigger on the oscilloscope, and I also have an analog output accelerometer that's also wired to my oscilloscope, so I can see exactly where I need to add weight or remove weight from the rotor in order to bring it to balance. Okay, so I'm going to go ahead and spin up this rotor, and we should see somewhat sinusoidal waveform from the accelerometer and a pulse indicating exactly where that's happening from the Hall effect sensor. So I'll hit the run stop when I feel like I've got a good waveform. All right. So as you can see, I've got about 28 milliseconds between each of the pulses, and the peak of the pulse is happening around 8 milliseconds. So we can basically take that 8 divided by the 28 milliseconds and multiply by the 360 degrees to figure out exactly where I need to add the weights. I added 2 quarter-ounce weights where I thought would be the most applicable. Okay, so we can see there's been a dramatic improvement, and that amplitude is significantly reduced, and that amplitude is significantly reduced, and it does seem a lot more balanced now. I mean, the board is barely vibrating. It is still vibrating, but let's see if we can reduce that further. I haphazardly mounted the rest of the components needed to test the board with zip ties, super glue, P clamps, and whatever else I could find, and it was time to see how she does. Well, that's not very good. Let me adjust the timing of when the motor stops midair to see if it'll improve it. Nope. Seems like the braking function in the motor just can't stop the rotor fast enough. I designed a brake for the rotor using a servo and a piece of a band clamp, which is a type of cable-driven clamp for go-karts and mini bikes and things like that. I was really excited that the board was able to do this trick in this state, but now I needed to rebuild it so that I could ride it. I started by 3D printing some custom housings to house most of the electronics and to give my feet somewhere to stand. They also left a recess in the top for my display panel. I started with a brand new skateboard for looks mostly, but the skateboard's wider and gave a little bit more room for some of the other components. Here's some footage of me assembling the new configuration of the skateboard. So I set up the LCD screen to reflect the position with respect to pop shove it versus kickflip, and for the power that's applied before the trick gets armed. With the new board assembly complete, I went back to testing and adjusted some of my settings until I was able to achieve a kickflip again. Now we're ready to see if we can do it while riding. It was immediately apparent that I left some delay in my code on accident because it felt impossible to predict when the skateboard would ollie when I pressed the button on the remote. I damaged the board beyond repair in the field and I had to take it home. I went out for another day of testing with a repaired skateboard and an updated code to hopefully land this trick. I never quite landed it after many attempts. It still didn't feel quite right timing the remote with when I was jumping. I got back to working on lightening the unsprung weight of the trucks and the wheels. So I wired 2 limit switches, one on either side, in parallel, so that if either switch goes off, the board will be triggered to jump. I think it almost had it.
Cinematic shot.
Alright, let's give it another go. This ended up working quite well, and I was able to put together a couple sloppy landings on my next day of testing. Overall, this project was more challenging than I thought, and I'm pretty happy with the result. If I were to do it again, I would probably go for a slightly larger flywheel, and I'd spend a little more time optimizing the design of the ollie mechanism to get a little more vertical height. Thank you for watching. If you enjoyed this build, please consider subscribing. I plan on putting up similar builds to this one in the future.